I can share my slides, then we start today. So today, once again, welcome to this seminar. We do this every 2 weeks, and we've been doing, I think this is about the 10th or 11th that we are doing, and we plan to keep it running until the end of the year to cover some questions regarding the maths Olympiad and some topics from the curriculum as well. So today the plan is to work with the logarithms. We'll go briefly through the basics. That won't take too long. Then we jump into some questions. Try to solve some questions. I'll try to share my screen now, so that. So can you see my screen now? Are the slides visible on your end?
Yeah.
Okay, that's good. So we'll start the class. So the topic is logarithms, and we'll start with the definition. So to define this, we need to state a few things first. We need two numbers, A and B, which are both greater than 0, and we require that B should not be equal to 1. So we make the following claim that the logarithm of A to the base B will be equal to x if and only if A is equal to B raised to x. So this is the definition of the logarithm. On the one end, we have what we call the logarithmic expression, and on the other end, we have the index form or the exponential form, depending on which term is preferred. So as usual, we just say that under these circumstances, we say that the logarithm of A to the base B is x. So this again talks about the logarithmic form of the expressions and equations. And the next one just defines the index form or the exponential form. A is equal to bx is a index form, and logarithm of A base B is equal to x is the logarithmic form. So we should be able to switch from one form to another comfortably. So when we work, when the base is 10, so for instance, when B here is equal to 10, we call them the common logarithms. This, I think there are even tables for that. And then when the base is equal to the Euler's constant, then we call them natural logarithms. The Euler's constant here is given to, I think, 11 decimal places. Yes, I think 11 decimal places. The Euler's constant is an irrational number, so it has an infinite number of decimals. It can keep going on and on. What we have there is an approximation. So the logarithm can take on any value, any real number. So the logarithm can take on any possible real number. But it cannot act on numbers which are less than or equal to 0. So you cannot get the logarithm of 0, and you cannot get the logarithm of negative numbers as well. But you can get logarithm of positive numbers, and the values of the logarithms can be any possible real numbers. They can be from negative infinity to positive infinity. That's the domain. If you think of it as a function, the domain is the whole set of the range is the whole set of real numbers. Yes, Jeremy, you have a question?
Yeah, would it be accurate to say that in some cases you can find the logs of negative numbers, provided that the base is also negative? Like if you're given, say, negative 27 and the base is negative 3, then the log of negative 27 base negative 3 would be 3, no?
Um,
But in like very special cases, because if we were to change that to be the log of 81 base negative 3, then that would be possible because it'll be to the power 4, which will make it positive 81, meaning that won't be possible.
we you can work with the discrete logarithms, but you'd have to work with the modular arithmetic if you're going to work with discrete logarithms.
How so?
I would rather avoid that because if you are working with a function, you want the domain to be continuous in this case. So if you have a discrete domain where it jumps from one number to another, that requires a different kind of mathematics, and that's where you work with the discrete logarithms.
Oh, I see, I see. Thanks.
Yes. So we will not be looking at discrete logarithms. For that, if we do that, we must first do the modular arithmetic, which is not part of the talk today. So it will be a bit confusing if we put that. So but I hope your question is answered.
Yeah,
Jeremy?
fully. Thanks.
So here are some examples just to play around with the definition of the logarithm. If 8 is equal to 2 raised to 3, then we can say that the log of 8, the base 2, is equal to 3. This is just straight from the definition, so it's not anything. What follows the same? If you have 0.01 is equal to 10 raised to negative 2, so we can say that a log base 10, 0.01 of 0.01 is negative 2. So usually when you're working with the common logarithms, you can omit the base. So log 10 sometimes is just written as log without the subscript. But for emphasis now, for clarity now, we'll be including the subscript here. Here's another example. If 1, we know that 1 is equal to 6 raised to 0. So we can claim that the logarithm of 1 base 6 will be equal to 0. And this is true for any base. The logarithm of 1 to any base, any of the positive real numbers as a base, will be equal to 0. So here is another example again. We use the properties to solve the following. Find the value of x when the first one says when x is equal to logarithm of 64 to the base 4. Maybe you can make some guesses here. This should be easy. So the first one will be, we'll just go to the solutions, I think. So if x is equal to log of 64 to the base 4, it means 4 raised to x will be equal to 64. And that means x must be equal to 3. Again, just making use of a definition. Again, here, if x is equal to log of 0.0001 to the base 10, it means that 10 raised to x should be equal to 0.0001. And that means x must be equal to negative 3. Again, just from the definition.
Wait, wouldn't that be negative 4?
Oh, actually, you're right, negative 4. You'd have to go, yes, negative 4. That's a mistake. I think I added an extra 0 when I was typing.
I see, it's okay.
Yeah. I'll correct that in the slides. So the next one is log of 4 base half should be, means that a half raised to x would be equal to 4. And 4 is just equal to 2 squared, and 2 squared is the same as a half raised to negative 2. So that means x must be negative 2. Hopefully that makes sense. I believe it should. Here is another case where we just convert from the logarithmic form to the index form, and the solutions are here. If you have log of 125 to the base 5 is equal to 3, then this means 5 raised to 3 will be 125. Here, if the logarithm of 6 to the base 36 is equal to a half, it means it's the same thing as saying 36 raised to a half is equal to 6. That is just a square root of 36. So, and if you have it in variable form, the logarithm of y to the base x is equal to z, it means x raised to z will be equal to y. So this is basically just playing around with the definition. Now we can look at some properties. So if a, x, and y are positive real numbers, and we have a is not equal to 1, then we have the following rules. The first one is the product rule. The logarithm of the product of x and y is the same as the sum of the logarithms of x and y, and the logarithm of y. And the base remains the same. You have to stick to the base. All through you have base a. The quotient rule says the following. The logarithm of the quotient of x and y is the same as the logarithm of x minus the logarithm of y, all of them to the base a in this case. Then there's a power rule which says the logarithm of a of x raised to k is the same as k multiplied by the logarithm of x. And then the next one is the change of base logarithm. So if I have the logarithm of, if I know the logarithm to base a and I want to find the logarithm to the base b of the same number, this is a formula we'll use. Logarithm of x to the base b is the same as what I would know here is the logarithm of x to the base a, and then I'll need to multiply it by the logarithm of b, the base a, to get the logarithm of x to the base b. We shall prove all this. I hope I wrote that correctly. And another one that sometimes comes in handy, if you have a raised to the logarithm of x base a, it's actually the same as x. I think we'll prove the first four. The fifth one follows just from the definition of the logarithm. So we'll start with the first one. So if you have two numbers, x and y, positive real numbers, you can always write them as powers of a, where a is also a positive real number. So if we let x equal a raised to m and y equal a raised to n, then the product of x and y here is just am an, which is, if you use your laws of indices, if you have the same base, you can add the powers. So that am multiplied by an is the same as a raised to m plus n. So now we can apply the property of logarithms, because you know xy is equal to a raised to m plus n. If you follow the definition of the logarithm of xy, the base a, will just be this power, which is m plus n. But again, if you follow the definition of the logarithm, m here will be the logarithm of x to the base a, which is what we have here. And n here is the logarithm of y to the base a, which is what we have here. And that gives you the product rule. If you're getting the logarithm of a product of two positive numbers, this will be true. The second one is for the quotient. If again we use the same ideas and do, in this case, we do division instead of multiplication, and we find that x over y will be equal to a raised to m minus n. So that means the logarithm of x over y base a will be equal to m minus n. and we end up with the formula. So logarithm of x over y is the same as logarithm of x minus the logarithm of y. Okay. I think we are together there so far. Any questions on this? Okay, so the next one is a power rule. So if x is equal to a raised to m, then we can get xk, write xk rather as a raised to m raised to k again, which is using the rules of indices. It's the same as a raised to km, right? So that means the logarithm of this x raised to k base a should be equal to km, which is this. But we know that m is the logarithm of, based on this relation here, m is the logarithm of x to the base a. So we can write it, we can replace m with this logarithm of x to the base a. And we end up with a power rule where log of x raised to k is the same as k multiplied by the logarithm of x. So the change of base logarithm. So suppose x is equal to a raised to r. Then if we can get the logarithm of both sides of the equation with to the base b, so that on one end we have the logarithm of x to base b, and on the other end we have the logarithm of a raised to r base b. If you apply the power rule here, we will have log base x. Log of x is the same as r log b of a, but we know that r here, based on this relation, r is the logarithm of x to the base a, and we can replace r with this, so that logarithm of b x is same as logarithm of a x multiplied by the logarithm of b, logarithm of a to the base b. So this gives you the change of base formula for logarithms. You can rewrite it as, is this correct? Yes, yes. So you can rewrite it as this. This sometimes it's convenient to write it like that, but any of the two will work. So in the special case where x is equal to b, then you end up with this formula where log base a of b is equal to log base b of b over log base b of a. And log base b of b is also must be 1, so we can just write this as 1 over log base b of a. So these will come in handy, all these properties, as we go through the problems. So are there any questions on the definitions part? So we will see how you can apply some of these concepts when solving Olympiad problems from this topic. I will move to the problems now, unless there are any questions or comments on this section. Okay. So here we go. As usual, we normally give about 2 or 3 minutes for the audience to attempt the question or get some ideas on the way forward, and then we can go to the solution. If someone gets it right, they can share the answer. If they don't, we'll still go to the solution and share and compare with what they have. So I hope that is acceptable. So is there anyone who has made some progress, or we can proceed to the solution? So the problem says, suppose xy is equal to 144. And we are given that the logarithm of x to the base y plus the logarithm of y to the base x is equal to 10 over 3, where x and y are positive real numbers. We are supposed to find the value of x plus y. So we can move to the solution. So it may be a good idea to note down what is in the problem so that when we got the solution, but I think I've captured most of it. So this is given 10 over 3, I think that's correct. We are given in the problem that 10 over 3 is equal to log of x to the base y plus log of y to the base x. So if you work with a change of base formula, then you can have if you want the log to the base yx, you can write it as log y over log x. Is that correct? Yeah, I think so. And then you can write log x, y base x as log x over log y. Now, it doesn't matter which base you use here, as long as it's the same throughout, right? As long as it's the same base. So we can assume this is just the common logarithm, the base 10, but it doesn't matter what you use here. So this ends up, one is a reciprocal of the other, because this is log y over log x, and this is just log x over log y. So this, one of these is a reciprocal of the other. If you take this one to be a, then we have a plus 1 over a will be equal to 10 over 3. So you can, if you multiply throughout by a, and I think by 3 as well, and simplify, you end up with this quadratic equation. So now that we'll factorize, you can double check that this factorization is correct. So when you factorize this, you end up with 3a minus 1 multiplied by a minus 3 equals to 0. And that gives us two options. A can be a third, or a can be 3. So based on the two options, we can conclude that log of y will be equal to 3 log x, or log of x will be equal to 3 log y, depending on whether we take a to be a third or 3. So, and then in each case, you can convert this to index form. So if log y is equal to 3 log x, it means y should be the same as x cubed. The 3, using the power rule, this 3 can come as a power to the x here. So this can be logarithm of x cubed, and that means y must be equal to x cubed. The same on the other end. If you have logarithm of x is equal to 3 log y, it means x is equal to y cubed. So also in the problem, we've been told that x multiplied by y will be equal to 144. And based on this, now we can if you take, for instance, if you take y is equal to x cubed, then xy is the same as x multiplied by x cubed. That would be x raised to 4 will be equal to 144. So that means that x must be the fourth root of 144. And since y is equal to x cubed, then y will just be the cube of x. That is one possibility. The other possibility is if you consider the second set, this possibility, then you have y is equal to fourth root of 144. The same ideas, but this time you take x is equal to y cubed. So you'll have y over 4, y raised to 4 is equal to 144, and that gives you these two cases where x is y cubed, and y will be equal to this fourth root of 144. The question asks us to find x plus y. In both situations, x plus y is the same thing. So we just need to consider one. Are you finding x plus y or x plus y over 2? I think there might be some variance with what I'm doing in the solution and what was in the question. So x plus y over 2 will simply be a half of x plus y. We already know the values of x and y. And you can play around with this in third form. So like the fourth root of 144, we have 12 squared in the bracket. So you can play around with that using the surds, and it will simplify to this. So you have 2 root 3 plus 24 root 3, which gives you 26 root 3. If you multiply by a half, you should get 13 root 3. So this one is just a question of simplification. So I think that is okay. Is there any question on this? So here we made use of the change of base formula and also worked with converting from logarithmic form to index form and so on until we got to the final answer. Hopefully it all makes sense. So I will move on to the next question. So this question says if the logarithm of the logarithm base 2 of the logarithm base a half times the logarithm of x base 2, the same idea as throughout. It's a bit hard to read all that. Each of them is equal to 0. So the only thing that changes in each case is the number. Here we have 2. Here 3 changes. Otherwise the outlay is the same. The same on here, the 5 is what changes, but each expression here is equal to 0. So the task is to arrange x, y, and z in increasing order from the smallest to the largest based on the information. So I can give a minute for the group to try out the solution. So maybe I can just go to the solution. So we will pick the first expression. So the logarithm base 2 of the logarithm of a half of the logarithm of 2x 2. This is crazy. I think look at this expression. Whenever I try to say it, I get it wrong. So we just work with it as it's visible. We equate all this to 0. So so if the logarithm base 2 of this expression is equal to 0, it means this expression here must be equal to 1, right? 1 is what will appear as 2 raised to 0. So this whole expression must be equal to 1. And that's what we do at the next step. Now, if the logarithm of this expression is equal to 1, it means whatever is in here must be equal to a half raised to 1, so that logarithm of x to the base 2 will be equal to a half, right? So now if you convert this to index form, this is a logarithmic form. If you convert this to index form, then you'll get x must be equal to the square root of 2. That is 2 raised to a half. So the square root of 2. Does that make sense? So using the same ideas, you will find that y will also be equal to the cube root of 3, and z is equal to the fifth root of 5. So the task here is to compare these numbers and see which one is bigger. If you have a calculator, of course, you can do this directly, but most in the exams, you're not supposed to use a calculator. So you would have to find a way of comparing them without using the calculator. So one way is to raise them to the same power. When they raise to the same power, then it's easy to compare them. But we do 2 at a time. So we first of all compare z and x. So if you raise z to 10, you will get 5 squared. And if you raise x to 10, you will get 2 raised to 5. So based on this, you can conclude that z is smaller than x. So at least we know z is smaller than x. So we need to choose another pair to compare. So if we compare x and y, you can see that if you raise x to 6, it's the same as 2 cubed. If you raise y to 6, it is the same as 3 squared. So from here, you can conclude that x is less than y. So if you were to write them in increasing order, z would be the smallest, followed by x will be the next largest, and y will be the largest. So that's how you'd order them. Of course, this would be quite easy if you have a calculator. You just plug the numbers in and you'll be able to see which one is larger. But as usual, our problems do not, the contest itself usually doesn't ask for calculators, so you have to find ways to do it without the calculator. Any questions on this? So this part for y is equal to cube root of 3 and z is equal to fifth root of 5 is simply obtained from the problem itself. The same idea is used for the first expression are used for the second and the third, and then you obtain those two. So this will be the last question for today. We have let x, y, and z be 3 numbers. We want all of them bigger than 1, and let w be a positive number such that log of w base x is 24, log of w base y is equal to 40, and log of w to the base x, y, z is equal to 12. So the task here is to find the logarithm. No. This extra sentence is not necessary. The last one is what is needed. Find the value of the logarithm of w to the base z. So this sentence, I think, doesn't make sense. It needs to go. This second last sentence should be ignored. Then here there's a spelling error. This should be find the value of log of w to the base z. So we can go to the solution. So we make use of this change of base formula, the last version that we had in our formulas. That is log of b base a is the same, rather log of b base a is the same as 1 over log of a to the base b. So if you apply that to we can switch the bases. We had log of w to the base x was 24. So if you get log of x to the base w will be reciprocal, which is 1 over 24. The same applies to the others, so that log of y base w will be 1 over 40, and log of x, y, z to the base w is 1 over 12. So our target is to find the log of w, the log of z to the base w. So here we should have log to the base of w. I think there's a typing error here. It should be log to the base of w here. The subscript is missing. So you can write z as xyz divided by xy. Remember, both x and y are bigger than 1. They are not 0, so you can divide by xy. There's no problem. And then if you apply a mixture, the quotient rule and the product rule, the product rule is applied to the bottom one, and the quotient rule is applied to the whole thing, so that you'll end up with this expression. Log of w, log of xyz base w minus log of x base w minus a log of y to the base w. But all these values are known. We have them up here. So we just plug them back into the problem, and we find that log of w, the base z, is 1 over 60. And now we can get log of w, sorry, this one, log of z, the base w, is 1 over 60. So if you use again the change of base formula, we can get the log of w, the base z, as 1 over the log of z, the base w, which is equal to 60. And that's what we were looking for. So you can actually play around with the index form and still get the same answer. This is just to make us use this change of base formula, but you don't have to solve it using the change of base formula. It's possible to play around with the indices and still arrive at the same answer. So that brings us to the end of today's seminar. If there are any questions, you are free to ask now. You can also share comments. For some reason today, a number of people have called and were not able to make it. But it's my hope that the session was useful and you have learned something. Or basically, hopefully you have had fun in the session. That's usually the target. Are there any comments? If you have any comments, just unmute your mic and speak. Pardon? Did someone say something?
Yeah, Patrick Mulei tu anasema ni asante.
Okay, asante sana Patrick.
Nimeingia nikiwa nimechelewa kidogo, lakini nimefurahi hiyo mahesabu mbili nimeona.
Yes.
Thank you. Be blessed.
Thank you. Any more questions or comments? I think we'll stop there for today.